Okie dokie, let's try this as a YouTube video. Was having serious problems with Zoom earlier. I don't know what's going on, but it wasn't working. But hopefully this works for us. Okay, so we had read the problem, but let's just go back up to the top. It says the disk shown above spins about the axle at its center. A student's experiment reveals that while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. At time t equals 0, the disk has an initial counterclockwise that's positive. Counterclockwise is in this way, and that is of course positive. Okay. Um, and it later comes to a rest. Okay, at time t equals t1. On the grid below, sketch a graph that can represent the disk's angular velocity as a function of time from t equals 0 to t1 when it comes to a rest. Okay, cool. Now, as I was saying before Zoom started acting up, we have linear motion and we have angular motion. All right. So, with linear things, we have position, we have displacements, we have, that's of course initial position minus, position minus initial position, that's displacement. Okay. We have acceleration, we have velocity, okay. We have time, all right. Those are all the kinematic things. We also have, we add in mass, we have force, okay? And of course, force is equal to, that's net force, mass times acceleration. Okay, cool. For angular things, we have, it's not position, it is the angle theta. All right, it is not initial position, it is the initial angle. It's not displacement, linear displacement. It is angular displacement. That is, of course, delta theta, which is, if this is equal to x minus x naught, this must be equal to theta minus theta naught. Okay? We have not acceleration, not linear acceleration, but we have angular acceleration. That's alpha. We don't have velocity. We have angular velocity. That's omega. Going along with angular velocity would be, of course, initial velocity. Of course, we have over here initial angular velocity. Time is the only thing that is one-to-one because time is time. Now, it's not mass when we're talking about angular things. Well, what is mass? If you recall, mass is an object's resistance to acceleration. Okay, what's more difficult to accelerate? Um, a a marble or a car. Okay, obviously it doesn't take anywhere near as much force to accelerate a marble than as it does to accelerate a car. All right, why? Because the car has a greater mass, therefore has a greater resistance to acceleration. So mass is an object's resistance to linear acceleration. What then must be an object's resistance to angular acceleration? Well, then that is simply called, if you recall, I, which is, of course, moment of inertia, which makes sense because inertia is an object's resistance to acceleration. All right. So for angular mass, we have moment of inertia. That's resistance to angular acceleration. All right. We don't have force in angular motion. We have what's called torque. All right. And if net force is equal to mass and acceleration, net torque must be equal to moment of inertia times angular acceleration. One more thing to add on to this, torque is equal to applying a force to a distance. Okay, so if I have a rod, okay, if I have a rod that can rotate about this point right here. So we have a rod that can rotate. Imagine it rotating around into the screen. So it goes into the screen, around, back out of the screen, etc. So imagine it's rotating this way. Okay. If I apply a 20 Newton force at this point, or a 20 Newton force at this point, well, which one will have the greater acceleration? Well, it's going to be easier to push it, just like if you imagine opening a door. If you open the door near the doorknob versus opening the door at the axis of rotation, well, it's much easier to open the door out farther away from the axis of rotation, okay? So we have a greater torque because we have a force, whether it be 20 newtons, it's going to be 20 newtons. We have a 20 newton force here, or a 20 newton force here. Well, we have a 20 newton force times the greater distance from the axis of rotation, okay, well, it's going to be a greater torque. So that is what torque is also equal to. So torque, net torque is angular acceleration times moment of inertia. Torque is also force times distance. That is the only equation that doesn't really line up one-to-one with linear versus angular kinematics and forces. Okay, so here we go. We have all of our angular variables. Okay, it's asking us to graph what the angular velocity is going to be as a function of time. Well, we know it begins at angular velocity is omega naught. It ends at 0, comes to a rest. So it does so at time t1. Okay. Now it exerts a constant torque. Okay, there is a constant torque. Well, what is torque again? Torque is the equivalent, the angular equivalent for force. Okay, so imagine it's like saying you have a constant force. Well, if you have a constant force, that means by definition you're going to have a constant acceleration. Likewise, if you have a constant torque, you're going to have a constant angular acceleration. Okay, we know it's coming to a rest. Okay, so that means since angular acceleration, well, acceleration, if it's constant, is equal to change in velocity over change in time. Likewise, angular acceleration must be equal to change in angular velocity over change in time. You don't have to go through all the stuff I've written. I'm just writing out so you all have a better concept. Okay, so we have a constant change in angular velocity. It's decreasing because it goes down to rest. Boom. There we go. That is our graph for A1, A lowercase 1. Okay. Now, just like with all graphs I've been telling you since the beginning of the school year, you have a couple of things. You have the point. Well, the point of this first graph tells us the angular velocity. It says so right there. The area of that graph will tell you the angular displacement, because the area will be the y-axis, which is angular velocity times time, which angular velocity times time will simply be equal to a change in angle. Okay, but you can also find the slope. The slope of this graph would be change in velocity over change in time. Well, hey, I already wrote that down right here. We have change in velocity over change in time. Okay, because we have our slope is rise of a run. Rise of a run. Our rise in this case is our omega, our angular velocity. Our run in this case is our time, t. So omega over time is angular acceleration. That means the slope of this first graph is the acceleration, the angular acceleration of what's going on right here. Okay, so that means when I graph for part 2, my angular acceleration, well, that means I simply have to have a negative value, because the slope of this graph, I have no idea what the slope is. The slope is omega over t. Okay, but I can't actually graph that. It's actually negative omega over t. I can't actually graph that because I don't have actual numbers for this, but I do know that it has to be negative. So let's just go ahead and say that the angular acceleration of this graph must be a negative value, and this be a straight line. All right, My apologies for that. But it is a negative value for the entire time because the slope of this graph is negative the entire time. Okay? Now, cool. That's pretty straightforward. No problems with that. Let's scroll down. Um, the magnitude of friction torque exerted by this is tau. Tau, not torque, is tau. Greek letter tau. Derive an equation for the. Let me make this bigger right here. Enhance. Enhance. And biggen. Make this bigger. Okay, cool. All right. Derive an equation for the inertia I, that's moment of inertia, of the disk in terms of torque, initial torque, omega naught, and time. And any other physical constants if they are appropriate. Now, that shouldn't be too tough. We already said that torque is equal to moment of inertia times angular acceleration. And you know what? We're looking for moment of inertia. So boom, we're looking for this variable right here. So that means that I, a moment of inertia, is equal to, well, torque, that's tau, divided by angular acceleration. All right, cool, no problem. Are we done? No, because we cannot have it in terms of angular acceleration. We have to have it in terms of course, it's because we can't have it in terms of angular acceleration because it's not in one of the variables they gave us. They said do it in terms of torque, angular velocity, and time. Okay, cool. Is there any way we can relate? We have moment of inertia, that's what we're looking for. Don't want to change that. We have torque. Hey, they said we can use torque. We have torque, no problem. We have to get rid of angular acceleration. All right, is there any way we can relate angular acceleration to these other variables? Omega naught in time? Yes, there is. Scroll back up. I just said that angular acceleration is changing angular velocity over changing time. So that means we have torque is equal to, moment of inertia is equal to torque divided by, I can replace angular acceleration with omega naught, all right, because you know it comes to a rest, divided by time, okay? And what I meant by that is since the final velocity is equal to 0, we know that change in angular velocity is equal to omega naught minus 0. Okay? I'm sorry, I wrote that wrong. Is equal to omega minus omega naught. We know that this is equal to 0 because it comes to a rest. Therefore, change in velocity is simply equal to negative omega naught. But we're only worried about magnitudes, so let's go ahead and just say it's omega naught. Okay? And when I say we're only worried about magnitudes, we're not worried about the sign. So I can go ahead and I can just put in omega naught in for the change in the acceleration. So we have moment of inertia is equal to tau divided by, again, we said omega naught divided by time. I need to simplify this. When I do, it means that moment of inertia is equal to why am I tripping? Okay, I'm sorry. Torque times time divided by omega naught. And that is our final answer for B. Okay, cool. In C, let's see, it says, in another experiment, the disk again has an initial positive angular velocity omega naught at time t equals 0. At time t equals 1/2 t, all right, so half the time it takes, 1/2 t1, half the time it takes for it to come to what should be coming to a rest. It doesn't come to a rest if you read the problem. Continue to read the problem. The student starts stripping oil on contact with the surface between the axle and the disc to reduce friction. Okay, so adding oil is going to reduce the friction. As time goes by, it's going to have less and less friction. Okay, friction is the force causing a torque. All right, Friction is the force causing it to slow down. Okay, if it's slowing down, that means there's an acceleration, but it's not just doing it in a linear fashion, it's doing it in an angular fashion. So that means there is an angular acceleration, a negative angular acceleration. If there is an angular acceleration, by definition, there must be a torque. Just simply the same reason as if there is a net force, there is a net acceleration. If there's an acceleration, there has to be a net force. Likewise, if there is a net torque, there must be a net acceleration. And if there's a net angular acceleration, if there is a net angular acceleration, there must be a net torque. So we have the force in this case causing it to slow down is the friction. Okay, obviously, since we're adding oil, it's going to be less and less friction, so it's going to be less and less of an acceleration as time goes on. All right, meaning if it's negative acceleration, that means it's going to slow down less and less. Okay, so what I mean by that is before, so back up, we had, where'd they go? Before we had this straight line right here. Let's see if I can get the mouse right there. We had this straight line going down, no problem. The force was constant. Okay, at half the time, all right, in this new experiment, at half the time, we're now going to add some oil. So let's just think about what's going to happen there when we add oil. There's going to be less of a force causing it to slow down. So if there's going to be less of a force causing it to slow down, then this will not reach a resting point at the same amount of time. Okay, it will be the same force between 0 time t equals 0 and time t equals 1/2. So this line should be, the first half of this line rather, should look the same, but the second half shouldn't be quite the same. Okay, so let's graph what that should look like. All right, so we know eventually, well, we know it's going to start right here, and for half the time, there is a constant negative torque slowing it down, all right, causing a negative um, angular acceleration. But then right here at this point, we add oil. So what's that line going to look like? Well, it's not going to be quite as steep, okay? In fact, we're adding more and more oil as time goes on, okay? So, I don't like that. Let me see if I can undo that. All right. It wasn't terrible. You have gotten some points for that, but I can draw it a little bit better. All right. So the slope at this point must be less. Okay. So already you can see it, that slope is less. But then also, just as important, we know that we're increasing the amount of oil. So the friction should reach about 0. Okay. And let's look what's happening. We said that the slope of this graph will be the angular acceleration. All right, so right here we have what's for all intents and purposes, a constant slope from here to here. Okay, a constant slope. Right, that should be a straight line. Okay, but then right here we add oil, and the velocity is still decreasing, but it teeters off, and you see that this line is becoming more and more straight. Okay, if it were to go off the graph rather, you can say, hey, eventually it does have a straight slope, or a horizontal slope. A slope of 0, because it can't slow down because there's no force of friction causing it to slow down. All right. So how is that going to reflect this graph over here for the angular acceleration? Well, we know that originally it has a negative slope, therefore it has a negative angular acceleration. Okay, but then we start to add oil. All right, and since we're adding oil, the net torque is going to, and remember, just think of that as the net force. Net torque is going to decrease. All right, there's less of a friction slowing it down, so that means there's going to be less of acceleration. That means Not less as in it becomes more negative. No, remember, negative simply means the direction. This direction in this case is slowing it down. So that means we have less of a force slowing it down. So that means we have to get closer and closer to 0. Because if there's no force, if there's no force slowing it down, that means the acceleration has to approach 0. All right. Kind of asymptotes off there because eventually, no oil will eventually, run out. So maybe it does, maybe it doesn't approach 0, but the idea is the slope becomes less and less negative. Sorry, the acceleration rather becomes less and less negative because the slope over here on the angular velocity graph, becomes less and less negative. Therefore, the angular acceleration becomes less and less negative, teetering out to 0. Okay, cool. Last but not least, D, the student is trying to mathematically model the magnitude of the torque exerted by the axle on the disc when the oil is present at time t is greater than 1/2. So he's trying to figure out what's going to happen after we add oil at this point. Okay, is there a way we can model it mathematically? Well, that's pretty simple. Let's see if I can find the actual. Where'd it go? Did I go too far? Where are the equations? Ah, oh, it's underneath here. I see. I have to bring it out. Okay. Oops. Struggling. Give me 1 second. No, I'm not going to edit this out because it takes about 5 hours for that to be edited out. So just bear with it. Oh, goodness. All right, let's make this smaller. Make you smaller. Okay. All right, so simple question. Which equation best models the torque after we've added oil? We have torque is equal to a constant times t minus 1/2 times t1. Okay, cool. And over here we have torque is equal to a constant divided by that. Let's just think about this. What do we say is happening? We said the acceleration is becoming. Oh goodness! All right, this is messed up. Let's just remember we said the acceleration is becoming more and more. This is going closer and closer to 0. That means acceleration is getting smaller with time. Okay, which one of these? The magnitude, rather, is getting smaller with time. Don't worry about the negative. Okay, which one of these equations reflects that? Well, we have a constant times time. All right, let's look at this equation for all intents and purposes. If we were to distribute it out, it would be C1t minus C1t1 over 2 for this one. Then over here we have, well, there's no need to distribute anything. We have, as time goes on for this first one, torque is increasing. As time goes on for the second one, we have torque decreasing because time is in the denominator. Okay, as time increases, this torque is getting smaller and smaller and smaller. All right, approaching 0. Versus up here, as time goes on, well, at time t equals 1, okay, it's going to be obviously a much smaller number than t equals, well, let's just say it goes on for 100 seconds. Obviously, it's much bigger as time goes on with equation 1, versus down here in equation 2, it gets much, much smaller as time goes on. So which one reflects a decreasing torque and thereby reflecting a decreasing acceleration that we graphed in the previous problem? Obviously, it must be equation 2. That is the correct answer. All right, folks. I'm going to upload this. Hopefully, you all understand what I said. If you have any more questions, just go ahead, shoot me an email. Shoot me a message on Schoology or Remind. All right, take it easy. Did I record? I hope I recorded.